this video, we're going to look at the multiplication of two complex numbers in polar form. So we've looked in the previous video at the polar form of a complex number, how to put a complex number into polar form and what it means. We're now going to look at how to multiply two complex numbers together if they're expressed in polar form. So we'll need to make use of the following result. So we say that for two complex numbers in polar form, we have the following equation. So let's take the first number, we'll call it R1 times cos theta 1 plus I sine theta 1. So the polar form, we have these two numbers, the modulus and the argument, the principal argument. Modulus here I'm calling R1 and the principal argument is theta 1. And then we will multiply this by a second number in polar form. So I've called that R2 times cos theta 2 plus I sine theta 2. And what does this equal? Well, it equals R1 times R2. So you start by multiplying the moduli together, and that gives you the modulus of the answer. And then we times that by cos of theta 1 plus theta 2 plus I times sine of theta 1 plus theta 2. So what have we done? We multiply the moduli and we add the arguments. So this is a very important thing to take note of, that if you multiply two complex numbers together that are in polar form, then you find the modulus of the answer by multiplying the moduli together, which is what you might expect. But the argument is found by adding the two arguments together, not multiplying. So it's not cos of theta 1 times theta 2, it's cos of theta 1 plus theta 2 and sine of theta 1 plus theta 2. So we're not going to prove why this is true in this video, we'll just take it as a given. It is true for any two complex numbers in polar form. This equation does hold, so we can use it to solve a question. Okay, so the example we're going to do is let z equal 3i and w equal minus 2 plus 2 root 3i. Write z and w and z times w in polar form. So we want to find these two numbers in polar form and find their product in polar form. For that bit, we will use the equation at the top. So the numbers are expressed in standard form, a plus bi. For the case of z, a is 0. We have 0 plus 3i. And for the case of w, a is minus 2. And b is this funny number 2 times root 3. It's an irrational number, but it's still a real number. So these are in standard form. So let's start by putting them both into polar form, because that's what we're asked to do. So easiest way to do this is to draw a diagram. Always draw a diagram when working with complex numbers, going from the standard form to polar form or the other way around. Easiest to draw a diagram. It doesn't have to be neat and straight like mine is on a computer. It's easy to draw it neat, but if you're just drawing it on paper, freehand, it's fine if it's not perfectly neat. You're just using it to help you solve the problem. So it doesn't have to be neat or 100% accurate, but let's just roughly mark a line here going up the imaginary axis because z is 3i, so it lies here at 3i up the imaginary axis. So I've not bothered to draw a scale onto my axes, but this sort of defines the scale. I'm saying this is 3i, and then w is minus 2 along the real, and then 2 root 3 up the imaginary. 2 root 3 is roughly, well, it's just bigger than 3, just slightly larger than 3, so I'll say that that is about here. I've gone about 2 along the real axis in the negative direction, and then slightly more than 3 up the imaginary axis, so this is my number w. So let's look at z, 3i, and try and calculate its modulus. Well, the modulus is just the distance from the origin, and we can see that that is 3 units, because we've gone 3 along the imaginary axis. So the modulus of z is 3. So the modulus is often denoted with an r, but you can also denote it by enclosing the number in these vertical lines. So when we use these lines, that means the modulus of the complex number, which as we have seen is equal to the square root of a squared plus b squared. We didn't really have to do that in this case because we can just see from the diagram, but if you did do that, you'd get the square root of 0 squared plus 3 squared, which is indeed 3. Okay, what about the argument? Well, that's the angle measured from the positive real axis in an anti-clockwise direction to the line going from the origin to the number. We can see again from the diagram that in this case that is just 90 degrees. So if the number lies on the positive imaginary axis, its argument is always 90 degrees, which in radians is pi by 2. So to denote the argument, we use this function arg of z, and it equals pi by 2. So I always use radians when talking about complex numbers, or at least I always use radians when talking about complex numbers. And okay, what about w? That's a little trickier. So, well, the modulus of w is equal to the square root of a squared plus b squared. A is minus 2 if you look at w on the diagram. So we square that, we get 4, and then b is 2 times root 3. We square that, we just square 2 and root 3, so that's 4 and 3. 4 times 3 is 12. So we get 4 plus 12, which is 16, and the square root of 16 is of course 4. So the modulus of w is 4. What about the argument? Well, let's construct this triangle. So if we look at the diagram, I've drawn this line in to construct a right-angled triangle, and we can use trigonometry to find this angle here, theta. Now this isn't the argument, because the argument is the angle measured from the positive real axis round to the line. But if we find this, we know we can find the argument by subtracting theta from 180 degrees, which is half the way round. We subtract theta from that, we get the argument. And 180 degrees is pi in radians, so we need to do pi minus whatever theta is. Well, if we put some values on this diagram, we know that the base of this triangle is 2, and the hypotenuse is 4, because that's r, the modulus, which we just found. And we know the base is 2 because we've gone minus 2 along the real axis. So you could use trigonometry now to find theta quite easily using SOHCAHTOA. We've got the adjacent and the hypotenuse. Or you could, without even having to do any trigonometry, you could make the following observation. So if I take this triangle and flip it over and draw an exact copy next to it, like this. So I've just drawn the exact same triangle next to this triangle, but flipped over down the vertical. Then what do I know? Well, I know that I've now got a new triangle, and the length of this side of it is 4. The length of the other side of it, one other side, is also 4, already marked on the diagram, and the base of it, well, if half the base is 2, then the base of it in total is also 4. So this is actually an equilateral triangle, all sides are the same length, which means all the angles are the same, and the angles in a triangle add up to 180 degrees, or pi, which means theta, one of the angles, is pi divided by 3. So this is a trick you can always do if you have a right angled triangle where the shortest side is half the length of the hypotenuse, which is what we had here. We had the shortest side 2 is half of 4, the hypotenuse. You can place another copy of the triangle with the same dimensions next to it in this way and get an equilateral triangle. So you'll always calculate that the angle theta here is pi by 3. So the argument, remember, is this angle here, looking at the diagram, this angle I've just drawn going from the positive real axis to this line in an anti-clockwise direction. Well, that's argument of w, and it's equal to pi minus pi by 3. Pi would be the whole half the circle round, but we take out theta, which is pi by 3, and we get the argument, so that's 2 pi by 3. So pi minus pi over 3 is 2 pi over 3. So let's write down what we have. We want to write the two numbers in polar form. So z is equal to 3, that's the modulus, times cos of pi by 2 plus I times sine of pi by 2. And you can hopefully figure out what w is going to be. W is equal to 4 times cos of 2 pi over 3 plus I sine 2 pi over 3. So we're just using the information we just calculated to write these things down. And now we just need to calculate their product, z times w. What is that? Well, we just use the equation at the top. So we start by multiplying the moduli together. In this case, that's 3 times 4, which we know is 12. And then we add the arguments together. So we just have to add pi over 2 to 2 pi over 3. So we get cos of 7 pi over 6 plus I times sine of 7 pi over 6. So just try adding pi over 2 to 2 pi over 3. Try doing it on paper. You can use a calculator if you want, but hopefully just get a common denominator, do it on paper, and you should find that you get 7 pi over 6. One final thing to note is that here, 7 pi over 6 is within the range 0 to 2 pi, which is the range I take the principal argument to be in. But if both the arguments of the two complex numbers were quite large, if they were both quite close to 2 pi, then when we added them up, we would get something outside of the range 0 to 2 pi. We'd get something larger than 2 pi. And if that's the case, you just need to minus 2 pi off them to get something within the range. So always just check that your argument you find is within the range for the principal argument, which is either 0 to 2 pi, or some people take it as minus pi to pi. And if it's not in that range, you just need to minus 2 pi off it to get it within that range. So this is our final answer for ZW, 12 times cos of 7 pi over 6 plus I sine 7 pi over 6.